Okay, let's see what we've got. It's an easy. Haven't done this one before. Let's do this. Count operations to obtain 0. You're given two non-negative integers, so 0 positive. In one operation, if the first number is bigger than or equal to the second number, you can subtract num2 from num1. Okay, so that makes it even that makes the first one smaller. Okay. Otherwise, subtract num1 from num2. Sounds like Euclidean factorization something, greatest common factor. For example, if num1 is 5, num2 is 4, subtract num2, so subtract 4 from 5 and get 1 and 4. Yeah, this is generally the operation. I don't know. Seems similar to like Euclidean factorization, finding relative primes or something like that. Return the number of operations required to make either num1 equal to 0 or num2 equal to 0. Okay, so 2, 3, this will make, subtract 2 from 3, so it'd be 2, 1, and then subtract 1 from 2 to make it 1, 1, and then subtract 1 from 1 to make it 0, 1, or 1, 0. So 3 operations. This one operation is 10 from 10. Okay. So let's do the simple way, which is just modeling it, or actually just doing it, and then see if there's a faster way. Answer equals 0 for, I guess, while num1 not equal to 0 and num2 not equal to 0. If num1 is greater than or equal to num2, num1 subtracted by num2, else num2 subtracted by num1. Answer increments. Return the answer after the for loop or while loop. Okay. I think this might be slow. Okay, so it's average. There is a faster way, a very fast way. Let me think. 3, 2, 2, 1, 1, 1, 1, 0. You do it without doing the operations themselves. Okay, let's say it's two random numbers. Let's say 13, 9. So it'd be 13, no, it would be 4, 9, which would lead to 4, 5, which would make it 4, 1, which would become 3, 1, 2, 1, 1, 1, 1, 0. Okay. Or 0, 1, either of those. I think once one of them becomes 1, the number of operations from there is the bigger number. So 4 decrements down to 3, 2, 1. Okay, so I think that might be slightly faster. Do they both start at non-zero? They can both start at non-zero. Guess I can break when either of them are 1 or less. Say, or if they're not equal, I think they eventually hit 1. So I can check for if they're equal first. Return 1 in that case, because one number subtracts the other number and becomes 0. Otherwise, I think eventually they have to hit 1. Think of a way that they don't hit 1. If it was like 6, 3, then it'd be 3, 3. Okay, so it's possible that if they don't start out equal, they do eventually hit equal. So like, okay, if they're a multiple of each other, if one's a multiple of each other, then the other one's going to be just, the answer is just going to be the division between them, right? So I guess maybe I can check if their like remainder isn't equal to 0. And if the remainder is equal to 0, then I break. Remainder of either a divided by b or b divided by a. And if it's equal to 0, then I break. And then I would return the division. And that will work if the one of them's 1. Maybe I can make them I want to do this so that I don't have to worry about a divided by b versus b divided by a. I just want to make maybe num1 be the bigger one, num2 be the smaller one. Num1, num2 equals max of num1, num2, and min of num1, num2. Or I guess that's probably more complicated than if I just say if num2 is greater than num1, then num1, num2 is equal to num2, num1. Just do a swap. So therefore I guarantee that num1's bigger. And I think here, while num1 divided by num2, mod, the remainder of num1 divided by num2 is not equal to 0. Keep on doing this. I think it'd be num1 subtracted by num2. And then same thing here. If num2 greater than num1, num1, num2. I think that's fine. And then I return, well, each time I do this, I increment answer counter. I return the answer, yeah, I think I return answer plus whatever the division gets me. Oh boy. 0, 0. I did not expect. Yeah, I should have caught that edge case. So it's not going to hit, the remainder there is 0. I think I just need to catch this edge case. Is that case actually? Yeah, the edge case is if either is 0, then return 0. I guess I could do, rather than do 2 conditionals, I can do if the multiplication equals 0, return 0. 0 product property. Well, I'm in this no man's land between extremely optimized and average-ish. Can I optimize even more? Yeah, I wonder if the if statement actually slows things down, to be honest. I can do if num1 mod num2 equals not equal to 0 and then I would have to check which one is bigger to subtract from anyways. So I have to eventually do an if statement somewhere here, I think. Make one. So if I didn't have this, it'd be, well, num1 mod num2 not equals 0, and num2 mod num1 not equal to 0. And then what? It have an if statement then. If num1 greater than num2, num1 minus equals num2, else num2 equals num2 minus equals num1, and do the loop again. I mean, seems worse. Alright, I guess I'll just try it. Can't hurt to try. Well, I guess it can actually. Okay, I think that's correct. Oh boy. Fudge. So what is it gonna do here? It's not doing it correctly. 2, 3. 2, 3. And the answer it gives is 1. 2, 3. So it does one loop. After the loop it should be 1, 3? No, it should be 2, 1. Oh, yeah, okay, yeah. This is assuming that num1 is bigger than num2. Fudge but it. If num1 is greater than or equal to num2, else answer plus num2 divided by num1. Yeah, it's all the same. I think I prefer just setting it up so that always num1 is bigger than num2, even if it's somewhat slower. Or, no. So it was like 6 milliseconds. I really want to optimize this further. Try for the mystical 0 milliseconds. Whatever. Congratulations to people who optimized that well. Okay. So summary here. As an aside, this problem is very similar to Euclid's method for determining, I want to say, determining whether two numbers are relatively prime. I want to say. Euclid's algorithm prime relative, I think, or is it greatest common factor? Greatest common divisor. And it's the number that eventually Euclid's method algorithm for GCD. What is this? Okay. Yeah, so if it becomes 0 and since the remainder is now 0, the GCD is the last non-zero remainder. Okay, last non-zero. So if it's 1, if it eventually hits 1 as one of the numbers, then that's going to be the greatest common divisor. Okay. Or the GCD between them. Anyways, I guess I really didn't do very much, right? Wait, what did I do here? Oh, yeah. The one shortcut here in the above work compared to doing the full simulation, the full process until 0 is reached is understanding that when the two numbers are when the numbers are such that one is a multiple of the other, the number of operations to get to 0 is equal to the div, the quotient of those numbers. For example, if the numbers are 20 and 5, the process will take 4 operations. Similarly, for x and 1, we'll take x operations. So instead of going the full, so have a short circuit stop to the loop when that occurs rather than hitting 0, which is the default. Count the operations appropriately and return. Okay, time complexity. This is going to be O of that's an interesting question. What's the time complexity here? How many operations? O of actually, not sure. It's very fast. But I don't know how fast. I think it probably is less than O of log k, where k is the max value. What is, okay, time complexity of Euclid's method or GCF? Okay, it's O of log of min of AB. So I wasn't too off. Where k is the max value. Okay, well I guess k should be the min value. Oh, I guess it's less than this, so I wasn't incorrect when I say it's less than that. It's really imprecise though. Okay, well, I'll just leave it at that. Okay. Googling it. Googling Euclid's method. It's O of log of min of AB. Which isn't too far from my guess. Okay, anyways, base complexity, this is going to be O of 1 since since no space is needed, no extra space.